Thank you very much. So thanks for the invitation, my first time in India. And so here that will be the point of view on very similar questions to the things you've heard from Mark, but maybe from a more mathematical point of view. In particular, of course, the link with spin glasses will be apparent, but the point of view here will be everything from a geometrical point of view initially. So like you would do physics at 0 temperature and then try to understand things from there, rather than the usual thing in physics, which is to understand the Gibbs measure and then let the temperature go to 0. So it's a more, I will start with a more geometric point of view on essentially the same type of questions. The goal is to understand the landscapes that you meet in high-dimensional statistics, high-dimensional inference, in machine learning, possibly, and understand their geometry, their topology, and then, of course, in the next phase, understand how you explore them, trying to find a minimum, say, but with plain vanilla algorithms, right? So the algorithms that you use in the real world of machine learning, that is, or optimization, that is, gradient descent, stochastic gradient descent, online gradient descent, this kind of things, and not the smart algorithms like BP, all right? So, in fact, those algorithms are a little dumber, and so they are harder to analyze. The goal will be to prove that in most of these hard problems, they do as well as the smart algorithms. Okay, so just a few words on the landscapes I'm mentioning. Of course, we all know these first slides are very easy. We all know that a common task, a common path to solve a statistical task, say, for instance, and this will be what I'll be concentrating on here, in statistics, one of the tasks is, of course, parameter estimation, which, of course, is the same thing as learning, is through minimizing a risk or a loss or maximizing a likelihood. So at this point, I will not go into how you find the loss, risk, whatever. I start from it. I'm not here frequentist, Bayesian, whatever. Just, you start from this, because in the end, that's what you have to do. So typically, you want to minimize. So if you prefer maximizing likelihood, add a minus sign, a negative sign to everything, okay? So you minimize risk or loss, so sometimes called the true risk or some of the population risk, which is usually given by the expectation of a loss function of x, and theta expectation here being taken on x, right? And then here theta is a parameter, I will choose it to be in dimension n. This is what you want to estimate. Very soon this theta will be an x, and you want usually to estimate it by minimizing this function. L is a loss function. So typically, if you do maximum likelihood, this is a negative of a log likelihood. Or anything you've built because you know how to build it. Like in machine learning, you build the architecture of a neural net, and this defines the L with whatever, an L2 risk. And X, of course, is the data, and I assume that X is, each X is in RD. So the hardest thing in this is to follow the dimension. So N is the dimension of the parameter, D is the dimension of the data. Okay, of course, obviously this population risk is unknown, you don't know it, you can't minimize it. So what you do is you have data, let's say Xi, and you have M, sample, IID, unstructured data, to come back to what Mark was saying. And then, of course, we try to minimize the empirical risk rather than the population risk. So the empirical risk is the same thing, except that instead of taking the average on X, because you don't know the distribution of X, just take the empirical average on your data set. Everybody is with me, I hope, at this point. So I've introduced the important data. Again, N is the dimension of the parameter, theta. D is the dimension of the data. The Xi's are vectors of dimension D. And M is the size of the sample. This has not been unified. So look at the literature, N, D, P are all in all sorts of things. So it's important to come back to that. So please remember N, the dimension of the parameter, D, the data, and M, the size of the sample. Okay, so the natural question are, first, the information theory question, a la Chandan, like Mark explained. So first, I didn't start from the real task. The real task was to estimate theta, but so is there any statistical procedure that can work? can I do anything good with any L, right? Or is there an information theory threshold? Second, of course, is the statistical question, or in machine learning, this would be the architecture question. Is the minimization of our R theta a good strategy to estimate theta? Right? You don't know. I could have chosen L to be 0, right? Finding the minimum is not hard. Okay, so of course, statistics, classical statistics, is hundreds of pages about telling you, for instance, that the MLE is optimal. The maximum likelihood estimation is optimal in this and that situation, and this kind of thing. So there's a huge work on when is it optimal to do something. I'm trying to talk at the same time for the machine learning thing and the statistical thing. All right, so that means, is our statistical procedure well chosen? Is this loss function well chosen? Of course, this depends on the structure of the distribution of the data, which I don't know. What is the performance? And if I'm ambitious, how to choose a near-optimal statistical procedure, something really good. And so in machine learning terms, this is the architecture question, right? Because building the network is indeed building the function L, right? The function L will be the output of your network minus your, let's say you're on supervised learning, minus your result, let's say square, okay? Okay, and then the next question is, of course, once you've chosen the statistical procedure, is can the minimization of this empirical risk be a good substitute for the minimization of R? So the first question is, the statistical question is minimizing R, is that a good idea? But then the next thing is that a good substitute for that? And in what regime for N, D, and M? Of course, this, in machine learning term, this is the generalization question. Right? That is, if I can minimize, I don't know yet if I can, but if I can minimize properly, what I find is it decently related to what I want to estimate, which is theta. And then, of course, you have the algorithmic or optimization question. How can one find the minimum of this, right? It's easy to say minimize, but how can you find it? So you have to choose the algorithm, of course, and then maybe find a guarantee, because I'm a mathematician trying to find a guarantee of the performance. So, and you have many choices, of course, of algorithms. Of course, in machine learning term, this is the training question. Okay, so we've seen the three questions. The Chandan type question, the information theory, then the statistical procedure choice, the generalization question, and then the training question. All right. So what is this problem mathematically? So forget, on purpose here, I've not written one example, right? Let's look at it as like, geometers. What are we trying to do? We're trying to minimize the function Rm, which let's say is smooth. Okay, Relu is not smooth, but smooth it. Let's say smooth, and it's a random function. Okay, why is it random? Of course, because of the sampling. So it's a smooth random function of very many variables, because of course I will assume that my theta is in dimension n, as I said, and n will be very large, right? So the question here is a question of geometry of random functions in high dimension, okay? So what can we say about this thing? So let's take a step back. I'm not a physicist, I don't know what a Gibbs measure is. I just want to ask, how do you attack this question? If you have a smooth random function, how do you attack the question of understanding its topology, its geometry, and maybe the performance of all sorts of algorithms to go down the landscape? Okay, are you with me? All right. So, of course, most often this function is non-convex, so its optimization might be difficult. Interestingly, if you open some books on some very recent papers, in fact, you see non-convex functions are not important, you can always regularize. Okay, not really true, but of course, if you take this point of view, then what I'm going to say is not really crucial, because the topology of convex functions are not really interesting. Okay, so the first element then is to understand the complexity, I will come back to the definition of this, of the topology or the geometry of the random landscape defined by this random function. Okay, so how do you define how would you describe the geometry, the topology of a function? Defined on a large dimensional space. or even on a two-dimensional space to start with, right? So we'll have to settle that. So to come back to physics, is there a glass phase, to come back to the vocabulary used by Mark? That is there a phase where you have an enormous number of local minima or critical points? Then you would, of course, call the landscape complex. Oops, sorry. And what is the topology of, for instance, that's a way to describe the topology. You look at the level sets, right? So you cut at a certain level, you look at, let's say, the sub-level sets, the place where the function is less than something, and you ask yourself, what is the topology of that? Okay. You see that this is an important question, right? If my function is like this, and I do that, the sub-level set is connected, right? It's one ball. My function does this, and you cut like this, you find plenty. So that's a very elementary way to describe topology, just the number of connected components, but you can do much better than that. Okay, so if you have, how many minima, how many critical points of all sorts of indices, and then the real question, of course, also is, are the deep minima, the one that are really, even if you have many of them, close to the true value of the parameter, we need to estimate. It could be that you have deep minima, it could be that you can optimize this thing well, but you can find an optimum which is deep, so the value is close to the minimum, but the place where the minimum is achieved is very far from the parameter you want to get. So remember, what? The true value of the parameter. There is a true value of the parameter. Let's say this theta is, you assume, of course, this is also part of this. You could do that, or you could not do that. This is very related to what Mark was saying. I'll come back to that. Okay, so that's the topological things. We'll have to see how we can describe these things. Then the next thing, which I'll come back in the next lectures, is to understand the performance of the natural algorithm to explore this landscape. Okay? Imagine you understand the topology, try to understand the dynamics in it. So natural algorithm, what do I mean by natural? Maybe SGD, online gradient descent, Langevin dynamics, if you want. And here you see not BP, not the a little smarter algorithm. These are the plain vanilla algorithm, the thing that you can apply directly. So what is the role of the algorithm? An important thing also, it's also where do you start your algorithm? Many of these algorithms, when you look at papers not in the math literature, of course, or the physics literature, and you look carefully, you will notice that many of the algorithms have a hot start. That is, in fact, you start not too far from what you want to find. And then the question is easy, right? So the important thing is to have an initialization. You don't know anything. You have no clue. You are in very high dimension, like Mark was saying, trying to find a point up there. You don't know where it is, and you start with something you can simulate, something at random, right? So when you have a very non-informed initialization point, that's really the problem you want to solve. And what is the role of the signal-to-noise ratio? Let's say the size of the data, right? More data, the problem will be simpler, of course. Okay. So let's go back to the topology. So a little bit of math. I won't spend much time. So the real question is the following. It's a very old question in math. It's, in fact, more than 100 years old. In fact, 97 years old. So take a smooth, real-valued function, think our empirical loss, on a manifold. Let's take it compact to make it simple. And n-dimensional, all right? Now you ask yourself, how can you understand the same question? How can you understand the topology of the landscape? So this is very well, this question goes back to the 20s and to Morse, Ashton Morse, one of the first, in fact, important US mathematicians. And so what is Morse? I cannot go into a class on Morse theory, but I will just tell you very quickly what the things are there. So questions are exactly the question I was asking. Can you understand the topology of the sub-level sets? You take a number u, you look at A of u, it's the point where the function is below u. So this is a set of dimension n, described in a manifold of dimension n. So describing the topology of such a thing might not be that easy. So for instance, one way you can, in fact, let me say what Morse does for those who know and otherwise just don't listen. The way to describe the topology of such a thing, so a sublevel set is something like a manifold in dimension n with boundaries, right? And the way to describe this is the topology of this are what is called the Betti numbers, okay, the homology class. So you have n Betti numbers, or n plus 1, depending how you count, and these are really the topological invariants of these things that the Morse theory will not give you in general, but will bound. Okay, so Morse theory in general will give you bounds on the possible Betti numbers, functions of the Betti numbers. If you don't know what the Betti number and homology is, a very simple thing is the earlier characteristic of the sublevel sets. So, for instance, that's one thing that maybe I can come back to and describe a little more. So the Euler characteristic is in fact an alternating sum of the Betti numbers, all right? And just to give you a preview of Morse theory, how do you compute that on any manifold? You take a non-degenerate Morse function, I'll say what that is, and you just look at this alternating sum of the number of critical points of index k, right? This thing does not depend on the function, it's a topological invariant, it's the earlier characteristic, okay? So, but let's come back to the question that looks more important for what we're discussing right now. Can we compute the number of critical points? So I will call crit f nk the number of critical points of f on the manifold M, which is in dimension n, of index k. So remember what the index is for a critical point. If you have a critical point, then you have its Hessian, and its Hessian is a quadratic form. You look at the number of negative eigenvalues, right? That's the index. The number of direction from a point, critical points where you can go down. Right, so the index of a minimum is 0, right? The index of the maximum is the dimension of the manifold, yeah?
You can classify modern surfaces, take volumes and accept
I'm sorry, I can't hear you.
Can you find topology of like volumes as well, like using Morse theory and it only for surfaces?
Can I find what?
Okay, I can ask.
No. So I didn't say yet what the results are. These are just questions for the moment, right? So this gives in four lines Morse theory. Okay, so of course very vaguely. It says Morse theory gives you constraints on these numbers in terms of these numbers, the number of critical points, in terms of the basic topological invariance, the Betti numbers, under the assumption that f is generic. Generic is usually called a Morse function, which means that the Hessian of f is non-degenerate at every critical point. So that's the nice functions for which you can understand things easily. That's the functions which are such that every critical point has a non-degenerate Hessian. So the Hessian is never the 0 eigenvalue. When you have this, every such critical point is in fact isolated. If you're on a compact manifold, you have a finite number of them, right? So the question of counting the number of critical points makes sense because you have a finite number of them. And so these numbers of critical points of fixed index, for instance, are, for a Morse function, there are constraints on them given by the topology of the manifold. So let's take a simple example. So I'm just doing that very quickly. Take the sphere, right, in any dimension. Then, so there's a difference here between even and odd dimension, but that's a small thing. What the Morse theory tells you for the sphere is essentially nothing. It says that you have at least, this constraint is to say that you have at least one minimum and at least one maximum, which is not a big deal. You don't need Morse theory to know that, right? And so typically the way topologists use Morse theory is the other way that we will do here. They want to understand the topology of a complicated manifold, not the sphere. And what they try to do is to find a Morse function that will satisfy the constraint very neatly. And then from this Morse function, which is a differentiable object, they will have information about the topology of the manifold. Right? Here we're not in this direction. Manifold is what it is, and we will see we are studying random Morse functions, which are not necessarily the simplest ones. So that leads me to the next thing, which is that simple functions are not necessarily simple. Okay, so in high dimension. High dimension is a trouble. So let's go there. Let's start with the simplest of all possible compact manifold, maybe. The torus could be another one. Let's take the sphere, okay, in n dimension. This is a very trivial topology. You don't have much to say about the topology of the sphere. All right. So take now a function f, which is the simplest possible function. What is the simplest function on a sphere? Take a polynomial. And even simpler, take a homogeneous polynomial. Right? If you take a homogeneous polynomial in degree d, in dimension n, you can of course restrict it to the sphere. Right? Because it's homogeneous. Once you know it on the sphere, you know it everywhere. So look at the homogeneous polynomial, say of degree p, on the sphere. It's hard to imagine a simpler situation than that, right? A simpler function and a simpler manifold. So that's a simple function, right? Okay. So the question is, how topologically complex can it be? So here, remember, I'm in the limit where I'm looking at a situation where p is fixed, say 5, and n is very large. Okay, so I take a polynomial, a homogeneous polynomial even, on a sphere in dimension 1,000,000. A polynomial is a simple thing, right? So how complex can it be? How many critical points would I have? The answer is it's not at all a simple thing. It looks like it's simple. If you take p equal 1, if you take a degree 1 polynomial, a linear thing, yeah, that's simple. How many critical points for a linear thing? On the sphere, 2, right? If it's a linear thing, which is the inner product with this vector on the sphere, you have the minimum here, the maximum here, and that's it. If you take degree 2, you have a quadratic form. You know very well that a generic quadratic form on a sphere of dimension n will have 2n critical points. What are they? They are just the n eigenvectors of the symmetric matrix defined by this quadratic form, plus and minus, right? So it's not very complex. Okay, you have n is a lot, but not very large. Oops. The problem is that as soon as you take p larger than or equal to 3, all hell breaks loose. Cubics are terrible. You take a polynomial of degree 3, it's a function that is extremely complicated. All right? So my involvement in all these stories here goes back to the fact that at Courant, at NYU, a long time ago, I was the dean. I founded the Center for Data Science, and I chose as a director a guy who was not yet as known as he is now, Yann Lequin. And at some point we discussed, I asked him, what do you do? Explain this very smart ways of minimizing things and so on. And then I told him, take a polynomial of degree 3 and try to minimize it with the best you can do at Facebook, then you won't be able to do it, of course. And he couldn't. So, in fact, this is an algebraic geometry question. Here is if you take a worst case thing, you take a polynomial, a cubic polynomial on the sphere, the maximal number of critical points is this. You see that when p is larger than 3, this grows exponentially. Right? So you have terrible polynomials on the sphere. Polynomial of degree 3, the number of critical points is exponentially large. And I can tell you the number of local minima is exponentially large. All right? But you could say, okay, so first there exists such a worst case polynomial. In fact, to my surprise, this has been proven in algebraic geometry only very recently. So the worst homogeneous polynomial of degree 3 are exponentially complex. The complexity, which means you take the log of the number of critical points, divide by n, here is roughly log of p minus 1, as you can see here. Okay? So this is a measure of caution. You should be careful because when even simple polynomials can be bad, you understand that your intuition about optimization in finite dimension has to be completely abandoned. All right? But this is a worst case scenario. Okay, that was the worst polynomial. So you can still hope that if you take a random polynomial, things will be good. Right? So let's be reasonable and pick the polynomial f to be generic, say random. Assume the coefficients of f to be, let's say, IID Gaussian. All right? Of course, you've recognized what I'm doing here. Yeah, but then this function is also exponentially complex when n diverges. So if you take it randomly, it's still bad, very bad. In fact, the anneal complexity of this is roughly half of the worst case. So it's not the worst case, but it's still exponentially complex. How do we know that? So this is what I will try to explain. How do you attack such a question? I give you an ensemble, a random polynomial, compute, or more general things, of course, because of course the landscape of inference are not random polynomials, but the tools are the same. How do you attack this counting question? How do you attack the question of counting the number of critical points, understanding the topology, the earlier characteristics of the level sets, all that? So there's a tool for that, which is called the Kac-Rice formula in math, plus random matrix theory. At this point, this should be mysterious. Why is there a random matrix question in what I just said? Right? I'm giving you a random polynomial homogeneous of degree 3. I look at this function on the sphere. I want to compute the number of critical points. And I say this boils down to a question of random matrices. So it's not easy to see where the random matrix is hidden. Okay? So I won't keep you guessing. The random matrix is simple. It will be the Hessian of this random function at its critical point. Okay? Because then the Hessian is will be a large dimensional, symmetric, real symmetric matrix. Large dimensional, random real symmetric matrix. That's a random matrix. That's the link between the two. Okay? So if you don't know about Kac-Rice, I will try to explain quickly, but I don't have much time. A very good book by Jean-Marc Azaïs and Mario Schwebor, or Robert Adler and Jonathan Taylor. Both appeared, this is an old thing. Kac-Rice, that goes back to the Second World War, where it's 39. Rice did it first in dimension 1, not in diverging dimension, and then Katz used it a lot just after the war in dimension 2. Right? So typically this is how it has been used, in small dimension. Here we're pushing it to large dimension. Okay? But these books are written in a general context and very good books. All right, so let's embark on this. Okay, in physics, by the way, Kac-Rice formula doesn't have a name because it's a triviality. Right? It's just obvious. So let me explain what the formula is, at least for what we want. There are many variants on it. I will give you one. So consider a smooth random function, f. Think our loss function, our risk function, or if you want to think of a simple geometric example, think of this random polynomial. On an n-dimensional, say, compact manifold, you can do that on non-compact. The version of the Kac-Rice formula we'll need now is the expectation of the number of critical points of my function f with index k, remember, with values in B. B is a subset of the real line. So here I'm computing something very precise. I'm counting how many critical points of index 3 with values between these two values, right? And that, of course, this B is important because when I'm interested in the level, the performance of my algorithm, I want to go deep, right? So this is given by the following integral that I will now describe. So it's an integral on B. B is a subset of R on the values. du is this integral. And then an integral on the manifold. You have this dx on the manifold, and you integrate two things. The first thing here, this ak, is the expectation of the absolute value of the determinant of the Hessian at x. Indicator function of the fact that the index of the Hessian is k. That's what I of x is. Condition by the value of f to be u, which is what you integrate here, and by the fact that f is critical. Okay? So you see here the random matrix. The random matrix is this Hessian conditioned by the fact that the function is critical and possibly by the value. All right? And so I is the index, and this phi here is the density of the law of the vector f grad f. right? So I assume things to be Gaussian, so this is a Gaussian thing, this is a Gaussian density. Everybody can compute that. That's not hard. The important fact is this one. Please note that you have absolute value here. That's the hard part. So physics has used this when understanding complexity of spin glasses, in fact, for a long time. The absolute value, when the problem becomes difficult, becomes a real problem. And physics, of course, has many things to do that, like supersymmetry, to get rid of this absolute value. I will not go there. I will do, what I will explain is really entirely contained in the word I understand. So if you forget the absolute value here, so you may not see that this makes the formula difficult, but the absolute value is really the hard part. If you forget the absolute value, this becomes much simpler. And now what you compute when you forget the absolute value, forget the index 2, is not the number of critical points, but the characteristic, the Euler characteristic of the level sets. Right? So when you forget the absolute value, you compute the topological object, which is the Euler characteristic, the mean Euler characteristic. When you put the absolute value, you compute the number of critical points. So it's not a trivial thing. Okay.
Why isn't the index of the Hessian determined? Why isn't the determinant of the Hessian sign determined by the index of the critical point?
Yeah, of course. If you do that, it is, of course. But then, if you don't fix the index, right? Of course, if you know the index, so the answer here is. But I wanted to insist on the absolute value. If you know the index, you know how many negative, how many positive, then you know the sign, right? So when you fix the index, you fix this, right? You don't care. The Euler characteristic is when you don't fix the index. Okay. In fact, there are variants of this Kac-Rice formula where you can compute higher moments. This compute the first moment, the expectation of the mean number of critical points. You can compute the second moment, third moment, so you can compute the variance, you can try to compute the dispersion, and you can also compute the Euler characteristics and more complicated objects. Okay, so the important message in this formula is that this Kac-Rice formula in high dimension is a link between the question of random geometry, topology that we are looking at, and question of random matrix theory. So the link with random matrix is what I just said. The formula reduces the study of the, let's say, the moments and the number of critical points to the understanding of the distribution of the absolute value of the determinant of the Hessian. Right? So the Hessian, as I said, is the law, I assume have to be Gaussian. It's a law of an n by n Gaussian random real symmetric matrix. Okay? So that's my random matrix. But it's not a priori GOE. Right? It may be a complicated thing because this Gaussian symmetric matrix may have correlation. Right? So the covariance structure of this matrix defines a 4 tensor, right? Which is the correlation between the entry ij and the entry at KL. Right? So you have a certain 4 tensor, which you can compute by differentiating the covariance function of f plus some linear algebra. So, in fact, there is a map from the covariance function, which defines your function, to a random matrix model of Gaussian matrices with dependent correlated entries in general. This class of random matrices model is really hard in general, and there is recent progress by Laszlo Erdős in Vienna and his collaborators. Right? I won't go too deep in that because that would be too hard too long for this class. I will just choose simple examples. But for important classes of example, this random matrix model is tractable. So I will cover 3 classes of example. First, the spherical spin glass, which has nothing to do with inference, but just to relate what I'm doing to the lectures before on glasses. The question of tensor principal component analysis, or spiked tensors. And then, which is more recent, the question of generalized linear models, or generalized regression, as Mark called them, the one-node networks we've seen, perceptron, perceptron lag, teacher, student type of things. So you see there are many, yeah?
About general relativity of random matrix theory.
Yeah.
There is one point that is reduction in some sense. You have a random matrix for the Hessian of one.
Yeah.
But this random matrix, it might be correlated with the random matrix of the Hessian of another problem.
Absolutely.
So if you just compute the expectation value of the number of points, it doesn't matter. But the statistics of this number.
So Mark, of course, is right, and experience in spin glasses helps here. Of course, in fact, it's not a random matrix. It's a field of random matrix. And it's really crucial. So you have a random matrix at every point, if you condition by the critical point to be, by this point to be critical. So you have, in fact, for every point, you have a random matrix model. And you're right, they are correlated. So this is not apparent when you compute the annealed complexity, which is what I said here, the first moment. But as soon as you want to compute the second moment, for instance, to say that the annealed computation is reasonable, because it could be that the annealed computation is completely nuts. As soon as you want to compute the second moment, the Kac-Rice formula gives you, which I didn't write, is of the same type, but with two matrices. And then if you want to compute the third moment, you have three matrices. So you have to understand, on top of the correlation inside the matrix, the correlation between the different points. So Mark is right. This is one more difficulty which I try to sweep under the rug. Okay, so, but I come back to that, in fact, for the spin glass model. So Tensor PCA, I will spend some time on that, is a very nice model, which is a hard model, which is a good model to illustrate many of the things that Mark said about planted model, right? And where we will see all the transitions there, interesting transition. Okay, so of course we hope to understand more loss functions which are more complex. This is a one node network. So that's still a little ridiculous, but it's still vast, contains a lot of statistical model. Of course, we have to go further and put many more layers, okay? Will come. So let's go back to spherical spin glasses. Example 1. So what is a spherical spin glass? It's this. The Hamiltonian of, let's say, a pure p-spherical spin glass is defined, so for physics, the sphere is always radius square root n. Right? For math, it's always radius 1, but we can switch. Okay, so it's this. Sum over ji1 ip, xi1, xi2, xip. Well, this coupling constant are id and 0, 1, you normalize properly. Okay? And so that's the Hamiltonian, what you do in physics, and this is a simple spin glass model, well understood. You compute the Gibbs measure, exponential minus beta h, and you try to understand this using whatever, the cavity, the replica method. And in fact, in this case, you can even have, because the literature in spin glasses in the last 15 years, there's been a lot of progress in math, in fact, to establish that properly, essentially based on the cavity method. No progress on the replica method, which is still a mystery. But the cavity method is essentially what has been used by Talleyrand, Penchenko, and others to roughly, I won't go there, but to roughly establish the results that are natural in physics. And then but if you want to understand that, you know, the Talleyrand book is that thick, so it's a long story. I won't go there. But so here, this is what so for this, physics tells you everything. You have a critical temperature above which this model is replica symmetric, under which it is, below which it is 1 RSB, 1 replica symmetry breaking. And you can understand precisely the distribution. So 1 replica symmetry breaking means that if you take 2 points under the Gibbs measure at random, their overlap will be either, in fact, in this case, either 0 or a positive number. Okay, their angle, if you want, on the sphere will be either orthogonal or a certain positive number. All right. So, of course, this model, you understand, is exactly the question I was mentioning before. This is just the thing I was talking about. This is a random homogeneous polynomial of degree p. Okay? So I'm back to this abstract geometric example, which is in fact the first example studied by physics. Okay? So for this, let me summarize, and I will just mention recent results on the math side. The physics side is much older but so these results are recent. So we understand the annealed complexity, the number of critical points of this thing, and it's exponential. So at fixed index below a given level, this can be described very precisely. So you can understand the number of local minimum, the number of saddle points, the number of critical points of index n over 3, if you want. And you can understand the topology of the level set. The quench complexities are now understood at very low level. So this comes back to the question by Mark. the annealed complexity that I give you, the first moment, can be entirely understood. But then if you want to really understand the complexity itself, you need to understand the quench complexity. So one way is to compute the second moment, right? And to compute the variance of the number of critical points. And this can be done. And precisely as Mark was asking, now you have to understand the correlation between two different points. This has been done, in fact, by Eliran Subag, his PhD, a postdoc at Courant, a former student at Weizmann. And from there, you can understand now the global minima, the lowest local minima in general. And you can understand from there and there, you understand rather precisely the structure and a much more detailed picture, in fact. So for the moment, it's temperature 0. You understand all the structure of the deepest local minima, their Hessian and all this kind of thing. All that is now completely clear. It's a lot of work, but it's done. Okay, so why is that possible? For the following trivial reason, that if you look at the Hessian of this thing, the J's are Gaussian, right? So this function is a Gaussian function. If you look at the Hessian of this, the second derivative, and you condition by the fact that the function is, that the point is critical, you will see very easily by symmetries that this Hessian is in fact a GOE, shifted by a value which depends on the level. So the Hessian of this is a GOE minus a constant times identity. Okay? A Gaussian orthogonal ensemble. So that's the simplest of all possible random matrices, and you know a lot about it. So in order to do this, so you use Kac-Rice. Kac-Rice reduces the problem to a question about GOE. Then you look at what the question is for GOE, and then you see that you need large deviation principles for the bulk of a GOE and for the edge eigenvalues. All these have been already proved 20 years ago, right? By Alice Guionnet and myself for the bulk, and by Alice Guionnet, Amir Dembo, and myself for the edge. So you have all the tools, because in fact, the GOE is a simple object. Okay, and when you put all the tools together, you get a very, very detailed picture. All right? This picture is interesting. I mean, this gives you something about, again, the geometry of the Hamiltonian, and I haven't used anything from the Parisi picture, if you want. I'm not doing this at positive temperature. I'm not assuming anything like I know a priori that the overlap should be like this or that. And I don't even know that the overlap is an interesting parameter. Okay, this is brute force. But once you have it, you can go from this 0 temperature. This is not where I want to go, because this has not much to do with the rest. But from this, if you are curious, you can go from this understanding of the geometric structure to the understanding of the Gibbs measure, the Boltzmann measure at low temperature. So this approach is exactly the contrary of what you do in spin glass theory, where you have, you start with understanding the free energy as a function of temperature. You describe it as a variational problem. You understand what the variational problem means. It's the overlap distribution, and then you try to understand what happened when the temperature goes to 0. So here you start from temperature 0 and you go up. Okay? And so there are recent works. So for instance, understanding precisely the bottom of the energy landscape gives very sharp information on the Gibbs measure at low temperature. For instance, you can see Subag in 2017. So for instance, here you can really see, of course, this detailed information will of course give the physics, the well-known things in physics, which is that the overlap structure, that you have, the overlap is hierarchical, that you have one RSB, one replica symmetry breaking, but it gives you much more. It really tells you that the Gibbs measure is concentrated on random circles on the n-dimensional spheres, which is a finite number of them. For instance, this very detailed thing, so this is what I'm saying here. It gives a very precise geometric picture of the one RSB. For instance, it implies that for the pure case, that there is no chaos in temperature. Right? For those who know what that means, it says the following. Here's a picture. Of course, I cannot draw, like Mark, I cannot draw in dimension n. So this would be a sphere in dimension n. Okay, that's the best I can do. And then what you find here is that you find that the deepest minima, you can describe exactly their height, their values. They are distributed randomly. You take the 17 deepest minima, they are distributed randomly on the sphere. So you have here maybe the deepest, maybe the second deepest, maybe the third deepest, etc. Okay? They are, of course, orthogonal on the sphere because they are chosen randomly. And what you see is that the Gibbs measure is concentrated at a given temperature on a little circle around it. Of course, this circle is itself a sphere. This sphere is in dimension n. So the sphere itself is dimension n minus 1. This thing are dimension n minus 2. They are still very high dimensional. And the Gibbs measure is really, you can prove that it's really concentrated on those things, which is, of course, the picture that every physicist has in mind when you say that the overlap has two values. How do you recover the structure of the overlap of two replica? Very easy. You take two replica, either they fall, you take 2 points under the Gibbs measure, either they fall in the same thing, and then their overlap is given by the radius, essentially, or they fall in two different ones, and then their overlap is 0. Okay? But this information is really very detailed. And why don't you have temperature chaos? It's because here, if I change the temperature, the only thing that will happen in a pure P spin is that I will stay in the same well. These corresponds for the energy to very deep wells. And then when you change the temperature, you raise the level, but you stay in the same well. So when you change the temperature, of course not too high when you stay, the only thing that will happen is that your radius will increase. Okay? But always centered on the same thing. Okay, so you have no temperature chaos, which means that the Gibbs measure at two different temperatures, two low temperatures, know each other, right? They have something in common. Okay, so where did I do with my, that's bad. What? Nope. What? Nope. Okay, sorry for that. Here. Okay, so you can go further with this. You can even study mixed models, which correspond to non-homogeneous polynomial. So for the anneal complexity, this is an old result, but there is recent work with Suag and Zaytouni and myself, where you find many things. For instance, in a mixed model, the structure is completely different. When you take a P plus Q model, you have temperature chaos. As soon as you have you take a P plus a Q and a little bit of Q, which means that the Gibbs measure are concentrated in, as soon as you change the temperature, the Gibbs measure are concentrated in completely different wells, right? So you see, this already gives you the intuition that this geometric analysis can be interesting. In the mixed case, a lot more needs to be done. For instance, we don't really cover full RSB cases. Okay? If you want to try, here's a nice problem. If you want to try using all this, take this very simple thing. Take a mixture of a degree 3 and a degree 16 polynomial. Right? P3 and P16. Take a mixture of the two. Our result here shows that when the mixture is close to 3, Mark smiles because he knows this example. When you're close to 3, this is a 1 RSB structure. This is what we prove over there. A structure like with this kind of picture here. When you're close to 16, 2. But in the middle, you're supposed to have, if you believe physicists, and I forgot who did that 20 or something years ago, probably Cavagna, I'm not sure. If you believe them, then in the middle you have a 2 RSB phase and a full RSB phase. Okay, so this trivial thing, mixture of two polynomials, already contains interesting thing. And this means that the Kac-Rice analysis will become really interesting there. Okay, so for those who want to try, I'm tired of it, but for those who want to try, this is an interesting open field. All right, so that was just to make the link with this trivial example. I took a random polynomial, which of course happens to be the spin glass. But now let's take something more statistical. Okay, nothing to do with spin glasses. So here's the model, the question, Tensor PCA. So we all know what PCA is, usual principal component analysis, but here I do it in a tensor context. So there is a simple tensor that is unknown to me. So here I will assume that this simple tensor, P tensor, is rank 1. Okay, to take the simplest possible problem. I could take rank 17, but I take rank 1. So rank 1 tensor has this shape. It's a vector v to the power p. Tensor power p, right? So this is the signal, the thing I want to understand. And it is noisy. What I have access to is, a sample of this vector, maybe multiplied by a constant, plus random noise, IID noise, right? So I'm not given the tensor, I'm given the tensor plus noise. So let's say V here is a fixed unknown vector. I have no prior on it. I assume that it's unit, so it's anything on the sphere, right? And the ZIs are random IID centered P tensors. This lambda has a signal to noise ratio. The objective is to, given those TIs, tensors, to detect, know if there is a signal or not, and to recover, that is, estimate V. Of course, I could ask the same question when the signal, instead of being rank 1, was low rank. But to simplify, let's do it with rank 1. Okay, so you understand the question here. Very simple. Okay, so let's assume that the noise is Gaussian, the entries are IID and 0, 1, no prior information on the spike V, on the tensor vector V. So my prior is a uniform measure on the sphere. So this problem is very well studied. So here is a lot of literature, Montanari and Reichmann and Zeitouni, Gay and Ma, Montanari and Richard, Florent, Jacques Alla, Laurent Lancas de Borova, and Perry, Vine, and Bandera recently. Okay, so this is an interesting problem. Okay, so let's go back to the 3 questions that I had. First, the Shannon question, the IT question, then the statistical question, and then the algorithmic question. Okay? So, okay, maybe first a simple remark. Let me go back to this. Here I have an M sample, I have M observation. Because I assume that the ZIs are Gaussian, we will see that I will reduce to the case where my sample is a size 1, but I can, by changing the signal to noise ratio lambda, it's essentially the same problem, as we will see. Okay, so for the moment I have this setting here, a signal to noise ratio lambda, an M sample, and my tensors are in P tensors in dimension M. So the first question is detection, which is the IT threshold, the Shannon threshold. If I give you those M noisy tensor, can you say that there is a signal in it, that there is this tensor V to the P in it, right? Or is it just pure noise? Can you make the difference between this tensor plus noise, between that and pure noise? All right? So can you make the difference between lambda positive and lambda equals 0? So one way to say that is what I'm saying here, the distance in total variation between the distribution with a signal to noise ratio and the distribution with no signal to noise ratio, with no signal, is it going to 0 or not? Right? If this distance is going to 0, it's bad news for you. It means the thing with the signal and without the signal are very close and you cannot separate them. The next question is, can you recover, what means can you estimate the V? That's what we call the statistical threshold. So there you could have many, many statistical approaches, right? So I'm a plain vanilla guy. I don't know BP, I don't know anything, so I just do what every statistician should do first, which is maximum likelihood. So you pick a statistical method. Here I pick maximum likelihood estimation, which of course is very easy. We're in a Gaussian context here. And but what's threshold for lambda is this estimator better than random? Is it correlated with the true signal? When is it converging to the true V? Because this would be called partial recovery. This would be called strong or full recovery. Perfect estimation, if you want. Okay? And then the third question, as we've seen, is computational. The algorithmic and computational threshold. Which algorithm will you choose and how will it work? So pick a computational algorithm, say gradient descent or SGD or Langevin. For what signal to noise ratio does it recover the signal? Of course, we want to recover in short time scales. We don't want to give the system an exponential time. Okay? So in short time scales, when is it that you can recover? With what algorithm? And again, here this is a plain vanilla statistical method, and now I want to choose plain vanilla algorithms. The thing that everybody would do without knowing anything. Okay? All right, so these are the three questions that we've seen. Let's go to try to understand that. So the detection threshold, so this is in the literature I've mentioned. With the proper normalization here, I don't know whether there may be a factor half somewhere, but this IT threshold is 1. Below this threshold, the two distribution with the signal or without the signal are indistinguishable. Their total variation distance goes to 0. So whatever you do, that's a Chandan type thing, whatever you do, you will not be able to distinguish them. The total variation distance, if you forgot what it is, between two probability distribution is the maximum of the probability of an event A for under P and the probability of an event Q, A under Q, P of A minus Q of A. You look at the maximum thing. So when the total variation distance is small, it means that whatever the event, whatever the observable you choose, the two values will be close to each other, and then you will not be able to differentiate them. Above this threshold, this distance remains asymptotically positive, which means that there exists one observable at least, where these two things are distinguishable, but you don't know which one. So of course, here we have chosen as an observable the maximum likelihood, the likelihood function. So question 2, the statistical threshold for partial recovery by MLE, it's the same. So this is extremely interesting and surprising. This tells you, of course, this threshold should always be above this one, right? Above the IT threshold, you know that there exists a good statistical procedure, but nobody tells you that MLE works as the best possible thing. So here, it says when it is possible to detect the signal, it is possible to recover it partially as soon as you can detect it. As soon as there's a way to know that there is a signal, you can in fact recover it partially by the plain vanilla method, by MLE. So by the way, this for me is not explained. I know we can prove that, but this is known. We could prove that this threshold is also 1. This is the same with the right units. Honestly, I don't understand why it works that well, but it's a fact. If somebody wants to that's a statistics question. If somebody wants to understand why MLE is the best thing you can do, that would be interesting, because the general theorems about optimality of MLE in this context are not easy to apply. Okay, the question 2 now, this question is in fact the place where the Kac-Rice formula is useful. This is the place to understand this MLE question. This is where you need to understand MLE gives me a loss function, an empirical loss function. We have now this random loss function on the sphere, and we want to understand its geometry. We want to say that the minimum of this is correlated with the true minimum. Okay? So for that, there are results about the complexity of this problem. This is the annealed picture, which is recent, with Andrea Montanari, Songmei, and Mihai Nica. And this is even more recent result with Valentina Ross, Giulio Bilori, and Chiara Camarota, where we do much more. Here we do the quench thing, but of course with methods that, as a mathematician, I don't condone. But of course the result is exact, correct, true, whatever you want to say. So in order to prove this mathematically, that the quench results are correct, we would probably have to do, if you want to do it rigorously, you would probably have to do what Subag had done for the spin glass, that is computing higher moments and work and deal with what Mark was mentioning, this correlation between different things. And this would be a lot of work, but an interesting one. But the truth is probably there. So let me explain before going there, or maybe I could first explain that. So what do we find before I go there? We find that using the Kac-Rice formula, so we find that the complexity is exponential. Right, so for this problem, you have exponentially many critical points, exponentially many local minima, But here they are. So this is the sphere in dimension n, the best I can do. I put the vector v that I want to estimate, that I don't know. Let me take it as the North Pole. Of course, I don't know where it is, right? It's up there. And so here you have the equator with respect to this North Pole. So what you can see is that there is a band around the equator. So first, or maybe I should wait because I need to show you a formula. Or maybe, let me give quickly and then I'll come back. You see that there is, when lambda is small, you have exponentially many critical points for this function, this log likelihood, and they are all in a band around the equator. Right? So that's not good news. Because it means that the minimum, the maximum likelihood estimator is close to the equator. Which means, if you take a point at random on the sphere, it will be on the equator with respect to v. A point at random on the sphere is fix a vector. A point at random in high dimension is on the equator. The equator has all the mass of the sphere. This is a very bad picture of the sphere in high dimension. A better picture of the sphere in high dimension would be this. This is the sphere in very high dimension. These are the two hemispheres, and this is the equator. Okay, that's how you should think. The hemisphere have very small mass, and the equator is very large. All right, so what we know is that all the critical points are on the equator. So in particular, the MLE, the place where the minimum or maximum is achieved, is somewhere here. And you want to be here. So the MLE will give you something which is exactly like random in this context. So very bad. Then when you increase lambda, the signal to noise ratio, at some point appears a band of critical points somewhere here, correlated with the signal. Right? And that's better. But then when you increase even more sigma, the global minimum shifts from being here to being here, which is good news. Because now the global minimum, which is your MLE estimator, is correlated with the signal. And when you increase even more lambda, the signal to noise ratio, this thing will concentrate more and more around that. So the estimation will become better and better. Okay? Okay, so let's move on to, let's try to explain why this is true. So first, before we go there, let's go at this thing. So the algorithmic or computational threshold. So you remember we had 3 questions. So what I was saying here, by the way, is the moment where the maximum likelihood estimator, the minimum, the absolute minimum, shifts from the equator to this parallel is exactly the moment of the IT threshold, right? Of course, when your global maximum or minimum is on the equator, you detect nothing, right? So but it happens exactly at the moment where you can do something. All right, so now the question is the computational threshold. So let's take with the simple plain vanilla algorithms. So what are this? So let's take, you can take Langevin dynamics. So you know what Langevin dynamics would be here. It will be to take the Brownian motion on the sphere in the potential defined by this function, right? Or you could take gradient descent or gradient flow, okay, or stochastic gradient descent. Any of these. But where do you, and you want to come close to this guy, or at least to correlate with it. So in my picture over there, you start from a random point in this flat thing, and you want to end up in one of those tiny holes, right? The 2 tiny holes are this hemisphere and that hemisphere. Okay? Of course, you start from a random point. You don't know where to start. If you do a hot start, if you start here, that's easy. But that's cheating, because in this picture it means you start from one of the tiny holes, right? Again, this picture is extremely misleading. Okay, so in fact, if you start from a point at random, you start at a distance, a small distance from the equator. When the radius is 1, you start at distance 1 over square root m. So the question is, you start from a point at random near the equator, and you do gradient descent or gradient flow or whatever, and you want to know whether you will get there. Okay, or there at least, in short time. So what are the obstacles for this to happen? Why is it difficult? First, if you look at the likelihood ratio, you will see that the derivative of the function you're trying to minimize in this direction is very small, because p is larger or equal to 3. The function in this direction is like this coordinate, let's call it x1 to the p. So its first derivative at x1 equals 0 is 0. Its second derivative is also 0. So your drift, the thing that is supposed to bring you to paradise, to where you want to go, is the function is 0, the derivative is 0, its second derivative is 0. So the drift is very, very small. Okay, that's why it's hard to leave this thing. So that's one thing, the drift is very small. The second thing is you have an enormous entropy here. Leaving this mass is very hard if you, let's say you have a Langevin thing, right? The third thing is, in this, the landscape is terribly bumpy. The landscape we will see is the landscape of a spin glass. This is your glass phase. So it's exactly the picture that Mark was drawing. If I look at the function here, it's like this, here near the equator, and when you go further, at some point it goes deeper around this point. But when you start around here, the landscape is really very bumpy. So you could very easily get trapped. Okay? So the real question is how to escape the equator, because once you have escaped the equator, between here and there, you have no critical point, and the drift becomes stronger when you're farther away. So you have a stronger drift, flatter landscape, nothing happens. You just go downhill. All right, so let's see that. And so the result that we have in this work with Reza Ghesari and Okosh Jagannath is that for this natural plain vanilla algorithm, applied to this plain vanilla statistical problem, so gradient descent, Langevin, SGD, they work in short time scales only when the SNR ratio is larger than n to the p minus 2 over 2. So this tells you this is a very hard problem. You need the signal to noise ratio, or let's say here it would be the number of data, to be very large, right? So you need an enormous amount of data to be able to do this. If you don't have this amount of data, we have a refutation. What will happen is that your algorithm will go around this thing because the drift is too small and there is so much room here to move around for long enough to find one of those guys. And then it will be trapped for a very long time. Okay? Yeah? So here, it's less than, we can in fact give the exact polynomial structure. It's, so we give it for the continuous time. For continuous time, it's finite. Okay, but then of course when you go to discrete time, it's just linear the number of steps. Okay, so this is good news because so you see there is a big, so that's exactly what Mark was explaining. Here we have 3 thresholds. I've seen your 3 thresholds, the IT threshold, the statistical threshold, and then the computational or algorithmic threshold. It happens here that these 2 thresholds are the same. The last one is huge. There's a huge gap. It's not a factor 2, it's a diverging factor. So this is a really hard problem. You need a lot of data to solve it. Okay? And by the way, if you took p equal 2, which is usual PCA, this vanishes. This is just constant. Because of course PCA is not a complex problem. Tensor PCA is. Okay? So interestingly, this threshold is the same for many other algorithms. The SMART algorithm, approximate message passing, that Mark was explaining. And this is a paper by Lucien et al. In 2017. There is lots of literature on the Florent, Chakala, and Kazdeborova in this direction. So again, these are smart algorithms. They use a lot of wisdom. These are stupid algorithms, and they work the same. It's much more painful to prove that stupid algorithm work well, But in the end, it's the same result. And this is due to the fact that this problem is really hard. And the thing you have to beat over there is really what I call escaping mediocrity. Right? You put a point at random, it's mediocre, right? It's somewhere on the equator. Escaping this is a really hard problem. And for that, not the detail of what you do, be AMP, gradient descent, or not, makes no difference, essentially. But this is a huge gap, and this is not the end of the story. So maybe now I can take your question.
So if it is so hard to find the factors, why does tensor factorization work so well?
What?
If you were to fit, let's say, a topic model as a tensor factorization problem.
It's not a tensor factorization problem. Here you have a spike tensor. You have a tensor and perturbed by noise, and you want to recover the tensor. And it doesn't work well. You need a lot of data. This is what this tells you. Right? Here I said with one example, the signal to noise ratio has to be n to the p minus 2 over 2. It tells you that m has to be larger than the power of n. I forgot which one.
So
okay?
factorization would have a totally different.
I imagine. I didn't study that, so I don't know. I imagine. This one is a hard one. There's no way to do it simply. You need a lot of data. Right? That's what it says. So of course it's not an interesting problem for machine learning. I'll come back to that. The cool thing about machine learning is that it works. So many algorithms. So probably this scenario is avoided. Okay? This belongs to the class I called of supercritical algorithm. The good algorithms are the critical ones. I will come back to that. These are hard problems. So undesirable, but still interesting. So in fact, there are less naive algorithms than these local algorithms, whatever they are, that work better. The threshold, the best threshold that is known is p to the minus 2 over 4. So better than this p minus 2 over 2. These algorithms are completely different. For a long time, they were essentially only the semi-definite relaxation, semi-definite programming, SOS models, sums of squares. And so this has been done, the SOS hierarchy. For instance, Bangalore did that. My colleague, former colleague, Afonso did that. More recently, you have this very interesting paper by Alex Wine, El Alaoui, and Moore, which gives a different algorithm based on what is called the Kikuchi hierarchy. And by Valentina, Giulio, and Chiara, this replicated gradient descent algorithm, which is, in fact, I think better. So it's based on our initial work together. Their idea is instead of throwing one guy trying to find the bottom of the landscape, you threw many of them on the sphere, replicated, and you let them collaborate once in a while. Because again, the only thing you need to do is to escape mediocrity. Once it's done, it's easy. Right? So maybe when some of these replica can manage to get a little bit of a boost, they can boost the other ones and collectively get there. Right? So this is an interesting, very recent but interesting possibility, because this is, again, in my view, in the category of plain vanilla. Right? It's gradient descent, but just boosted a little bit. These ones are rather subtle. These are very nice papers, in fact, and rather subtle things. Okay. So here you've seen these gaps. And by the way, this threshold here is supposed to be irreducible. There is no way, people really believe that there is no algorithm, a reasonable algorithm that beats this, right? Outside of a SOS. So being able to get to this threshold is really the best you can hope. All right? So let me explain how this works. When am I supposed to stop? 15, okay. So let's come back to why all that is true for MLE. I was a little fast, so I give you the results. Let's go back quickly to why this happens. So remember what we're doing. The estimator we find it obtained by, you take the empirical risk. So when you take the empirical risk, remember in our case, it was the negative of the log likelihood, right? Because I was doing MLE. So you compute the log likelihood for a Gaussian problem, that's very easy, and you find this. So the function you want to minimize is this. Since I had no prior, this is a function on U, which is on the sphere. So in fact, this thing, when you expand what Ti was, you find that this is this. The Ti was V to the P plus a noise, so it becomes this. But look at it. So assume m equal 1, because then you can change the lambda to lambda squared of m, makes no difference. So again, you can assume that v, your unknown vector, is in the direction e1. So this is my direction e1, the first coordinate. Then this function becomes just this. This is u1 to the p plus a sum. Here I'm put myself on the sphere of radius 1 instead of square root n, but it's the same thing. Of this. So look at this carefully. If you erase lambda, if you take lambda equals 0, if you have no signal, this guy here is just the spherical p-spin. That's exactly what it is. You're in a sphere, sum of IAD Gaussians, and this product. So this is the p-spin model. So on the equator, this is exactly the p-spin model. So this is now a p-spin model perturbed. So this is a homogeneous polynomial of degree p, which is very complex. This is a homogeneous polynomial of degree p, which is of course not complex at all, right? This one, the function u1 to the p on the sphere, has only, let's say p is odd, has only one minimum here and a maximum here, right? It's not a complicated function. So you have a very non-complex function perturbed by a very complex function. All right? Okay, so you apply Kac-Rice. So these are the questions we need to solve. Find if the global minimum is close to this North Pole here to check partial recovery. So this function is very complex and has exponentially many local minima, whatever lambda. Okay. So the question is where the global minimum, close to the signal, the North Pole, lost in the entropy of the equator. So of course you use Kac-Rice. And the random matrix problem that you find when you use Kac-Rice now, your problem is no longer a GOE, your random matrix, but it's a simple rank 1 perturbation of the GOE, right? Because you just look at it. So it's a rank 1 perturbation of the GOE. So okay, it's a little more complicated, but not that hard, so you can do it. So the question now is, when does the top eigenvalue of a spiked GOE, a rank 1 perturbation of a GOE, get out of the bulk of the spectrum? We all know that the spectrum of a Gaussian orthogonal ensemble is a semicircle. Now you take a Gaussian orthogonal ensemble, you add to it a rank 1 thing. Will this create an eigenvalue outside of this circle or not? Okay, that's the real question behind all this. It's this transition that creates the transition I'm describing over there, where this thing is going up. So this is well understood. It's called the BBP transition. And there's a long series of work. The question was first asked by Ian Johnston from Stanford. It started in this paper with Bike and Péché, and it has been continued by to serious depth. But the important result we need here is a result of 2007 by Mylène Maïda, who was then a student of Alice Guillonnet, which gives a large deviation principle for the top eigenvalue of such a spike thing. This is what you need. So when you do all that together, put all that together, you can find the result. So this is what I was saying. Close to the equator, the function is close to a pure spin glass. So it is complex there. When lambda is larger than 1, you have a ring of critical points which appears at positive latitude, as I drew over there, which contains the absolute, the MLE estimator. So this one was the critical thing. But now interestingly, the number of critical points on this ring is not exponential, it's sub-exponential. The complexity is 0, right? So to be honest, it's not completely clear. Even if you use the replica methods that we do with Giulio and Valentina and Chiara, it's not completely clear how many you have critical points there. You could have 5, or you could have log n, I don't know. But it's not exponential, it's sub-exponential. So the landscape on this thing is not exponentially complex. And when lambda grows, as I said, this ring is growing to this signal. So this is what is called asymptotic strong recovery. All right, so here's a theorem to explain all this, which is the one obtained by that. This is the anneal complexity. You can prove that the limit sup and the limit inf of 1 over n log of the mean number of critical points with value where, so this is the number of critical points such that the latitude x1 is in M, and where the value is in E. Okay? And this is obtained by a variational problem for a certain function, m and e, here on the closure, here on the interior. And this variational problem, this entropy function if you want, is given by this mess. Okay? So when you apply Kac-Rice, you apply everything you know about spike, the BBP transition, you put all that together, you get this. Okay? Which is a big mess. When you study this big mess, you find the phenomena I described. Trust me. Okay? Again, this is only the annealed computation. Somebody is courageous enough to do the second moment, third moment, and so on, we would be able then to bypass the replica computation, which of course my colleagues physicists don't want to bypass, but I would love to bypass it. Okay, so this was the number of critical points. You also have a result about the number of local minima. Okay, maybe I should. Yeah, so there's this interesting thing. You have when you look at local minima, there's an interesting transition. When lambda is smaller than a certain value, lambda 1, which I won't give here, there's an exponential number of critical points in a band near the equator, as I said, nowhere else. Then, when lambda grows, this band grows in width. But then when lambda gets above lambda 1, you have a sub-exponential number of critical points which appear at this latitude, away from this band, but the absolute minimum, as I said before, is still in the equator, not here. And then, when lambda is larger than lambda 2, the minimum is achieved at this higher latitude. And this lambda 2 is 1. So in fact, there is a phase, interestingly, there is a phase inside the Shannon thing, where Shannon tells you you cannot do anything. There's a phase which seems to contradict Shannon. There's a phase, this phase here, between lambda 1 and lambda 2, where in fact, you have a ring of critical points close to the signal. So you may think, with this, we could detect at least the signal, right? And Shannon tells you you can't. So there's something interesting. Of course, you can when lambda is above lambda 2, because then it's easy. You say, I look at the minimum. This is my procedure. I look at the minimum, the global minimum. It's in this ring. It's close to the signal. But in this phase, the global minimum is still at the equator. So you have, but you could say, but I don't care. I could look at the critical points. But of course, when you don't know where the North Pole is, you cannot know that these guys on the ring are on the ring of the North Pole. You have no way to detect the North Pole by knowing that these critical points. Okay, so that's the trick hidden behind this thing. Okay. Okay, maybe I should. That's what I was explaining. All these simple optimization algorithms are hampered by this problem, escaping mediocrity. So it's really important to, even in the simple phase of the topological transition, the weakness of the signal in the region of maximal entropy makes recovery impossible in polynomial time. So this is what I was saying, the drift is too weak. And if you wait too much time along the equator, you will end up trapped by the complexity for a very long time. So this question that you are either trapped by the glass phase or not is not really crucial. In fact, there is something more subtle. We've done the following. It's not in the paper, but we've done the following. Imagine that here I take this and I just kill the spin glass at the equator. Right? All these exponential critical points. I replace this by a smooth landscape. Okay? Still, it takes time to escape. If you start at random, it takes time to escape and get up there. It doesn't take an exponential time, right? But it's very long. The real problem for, let's say, for Langevin, the real problem is to escape a region of very large mass, entropy. And what happens is that, so this glass phase is not completely crucial. What happens is that glass phase makes things worse because it's hard to escape this. When your signal-to-noise ratio is too small, you go around, and then at some point, of course, you fall into in fact, you go around and down in terms of energy, and then you fall into one of those things, and then you're trapped for a very long time. But it's too fast to just see the glass phase as the problem. Entropy is already a problem. Escaping mediocrity is already a problem. Okay, and this I will keep for next time. So next time we will describe perceptron-like and generalized linear model with the same type of thing. And then in the last thing, I will tell you a little bit how proofs work for the dynamics, which here I just mentioned. But so just a word about that. Understanding the gradient descent, Langevin, or things like that, or online gradient descent, like Mark described this morning, rigorously in high dimension is really difficult. It's you need new analytical tools. It's stochastic gradient descent is understood since the 50s in finite dimension. The role of high dimension is really more complex. There are things which are not very well understood, so this is just the beginning. And so I will explain what we can achieve. There is still a lot of things to do there, just from the pure abstract point of view of do I escape mediocrity, do I go down, etc., independently of all the complexity. These are a different problem. For me, here is the question. There are different models that we introduced with Giulio and Chiara and Valentina, which we call the P plus K model. You can make variants of that, where here you would have an exponential complexity too. Right? So it's essentially the model I gave you. It's a spin glass plus x1 to the power k. A p spin glass plus x1 to the power k. And now you can play on k and p. Tensor PCA is k equal p. Right? But you can play on k and p. When k is small, smaller than 2, it's easy to escape the equator. Because your drift, which is the derivative of x1 to the k, right, the derivative could be 0, but its second derivative will not be 0. So when k is strictly smaller than 2, the problem is it's easy to escape. We don't have all this problem here. But then you may end up here with a pure complexity problem. You end up in this thing where you may have plenty of traps, and then of course you stay in one of those traps. When k is strictly larger than 2, like is the case for tensor PCA, because k is p, then it's extremely hard to escape mediocrity. This is what we see. So you need a lot of data or a lot of time. The interesting problems are k equal 2. This is what I call the critical problems. Because there, it's not too hard. It's not in finite time, but just a little more than finite time to escape mediocrity. Right? Your second derivative is 0, but just barely. And so you can escape mediocrity with a little bit more time. And these are our beliefs. So this we will see in this generalized linear model. These are what I call the critical problems. And these are what I believe the problem that machine learning is always solving. Of course, this is a very simple example, but there's an abstraction of this. Because in fact, when the problem is subcritical, any undergraduate can program it. Right? You go, you do Python and program gradient this SGD, whatever, and it works because the problem is simple. When it's supercritical, k larger than 2, you end up in one of those problems where you can't. Or you can if you have an enormous amount of data. So typically, the person trying to do that will go back to the boss saying, give me more data. Right? Because your problem will end up being on the equator, will end up giving you something random and without any interest. I believe that the interesting architectures are those that are just there, where because it's not too easy, not too hard, where in fact, what I call critical, where in fact you can escape with not too much time, not too much data, just increasing a little bit the data, and then you may face complexity, the glassy phase, when you arrive at the end. Here the problem, you have two problems. At the beginning of the trajectory, escaping mediocrity, and maybe one at the end, right? So that's an interesting story. By the way, just to close this, here is an interesting thing. So there's this question, it's obvious, right? Obvious, completely obvious that you need wide minima. It's better. Everybody says that. Because for generalization, wide minima are good, right? And you don't want to find steep minima. For me, I have no clue where this comes from. And interestingly, there are recent papers saying the same thing I'm saying now. Because in this case, the good minima, the one that will generalize well, are of course the one that you will find here. These generalize well, because now if you take another random set of data, you will end up in one of these. They generalize well because they're correlated with the signal. And if when the lambda diverges, it will be very close. Okay? But they are not wide at all. They are not wider than any other one. So this question of wide minima, for me, I have no idea where it comes from. So I was curious about that, so I Googled, like everybody, and then I found papers by Yoshua, Benjo, and others saying, wide minima, why? Nobody knows. So I'm not the only one to ask this. I think it's wise to not believe everything that is said in machine learning until it's probably true that wide minima are more interesting in some contexts, but I have no clue at all what these contexts are. In this case, at least, just an example. In this case, are not wide minima. The one that generalizes well are not wide. Okay, I will stop there.